Most people think more cylinders automatically mean better performance. But what if I told you that some of the most advanced engineering in the world comes from engines small enough to fit between your knees? In this video, we're breaking down why motorcycle engines punch so far above their weight, what car engineers quietly borrow from them, and where this philosophy completely falls apart. And if we're going to take it seriously, there's only one place to start: inside the engine. Because once you look there, the numbers begin to tell a story. Most people never stop questioning. The first number that refuses to be ignored is power relative to size. Not peak speed, not acceleration stories, not how dramatic something feels on a back road, just how much output an engine creates for every liter of displacement it occupies. Displacement is the one rule both motorcycles and cars cannot dodge. Take a modern 1.0-liter car engine, naturally aspirated and built for emissions compliance, smooth manners, and long service intervals. In most cases, you are looking at roughly 90 to 120 horsepower per liter. Push the tuning, accept some compromise, and you might touch 130. Now shift your attention to a 1.0-liter motorcycle engine. A Yamaha R1 with its 998 cubic centimeter inline 4 produces right around 200 horsepower. That is 200 horsepower per liter. No turbochargers, no superchargers, no laboratory prototype. This is a production motorcycle you can buy, insure, and ride home. That is not an outlier. It is the expectation. Even step down to a middleweight super sport and the math barely changes. 600 class machines routinely deliver power density that car engineers reserve for halo projects. To put that contrast in perspective, a Ferrari 458 Italia, revered for its naturally aspirated brilliance, produces roughly 127 horsepower per liter. That figure is celebrated in the automotive world. In motorcycles, it is familiar territory. This gap does not exist because car engineers lack skill. It exists because they are solving a different problem. Motorcycle engines are built around one obsession: extracting maximum output from minimal mass. When every pound counts, efficiency takes on a very different meaning. And once you see that pattern, a deeper question surfaces. Because those numbers aren't just impressive, they demand an explanation. Now, if this kind of engineering logic is the reason you love motorcycles in the first place, hit the like button, drop a little hype, and subscribe. Because that support is exactly what lets us keep breaking down machines at this level without watering it down. When people hear that a motorcycle engine spins past 14,000 revolutions per minute, the reaction is usually disbelief. It sounds reckless, like mechanical abuse disguised as performance, as if the engine is being whipped harder instead of engineered smarter. That instinct misses what engine speed actually represents. RPM is not stress by default, it is frequency. It simply describes how often the same sequence of events repeats. More revolutions mean more cycles, not automatically more punishment. The real question is what has to move every time that cycle repeats. Each revolution asks pistons to reverse direction, valves to snap open and shut, and connecting rods to stretch and compress. As speed rises, inertia becomes the enemy. Mass resists change, and once the forces involved exceed what the parts can tolerate, the engine reaches its ceiling. Car engines encounter that ceiling early because they are shaped for low-speed work. Larger pistons, longer strokes, heavier rotating assemblies. That weight delivers smooth idle and easy torque, but it becomes a liability as revolutions climb. Inertia ramps up fast, and the design runs out of margin. Motorcycle engines make a different set of decisions from the start. Their pistons are compact, stroke lengths are short, valve components are trimmed of unnecessary mass, the distances parts travel are reduced, and the weight involved in each movement is carefully controlled. This is not about aggression, it is about proportion. A shorter stroke means a piston covers less ground each cycle. Less travel means lower peak acceleration, which means reduced stress at higher speeds. Suddenly, revolutions that sound extreme become mechanically reasonable. The same logic applies above the pistons. Lighter valves respond faster. Compact valvetrain layouts stay stable as frequency increases. The engine is not fighting physics. It is cooperating with it. That is why 12,000 RPM does not feel frantic in a sport motorcycle. These engines were never meant to loaf at idle speeds. Their comfort zone simply lives higher. If you've ever ridden a bike that came alive only when the tach climbed, drop a comment and tell us which engine taught you that lesson. because real riding experience explains high RPM behavior better than any spec sheet ever could. And that leads to the real insight. Engines do not rev high by chance. That behavior is decided long before metal is cut. To understand why, we now look at the most fundamental choice an engineer makes: bore and stroke geometry. Every engine begins with a decision that never gets revisited: how wide the cylinder will be and how far the piston must travel. That relationship, bore versus stroke, does more than influence output. It locks in the engine's character before the first component exists. Most car engines favor longer strokes paired with conservative bore sizes. The reasoning is straightforward. A longer stroke gives the crankshaft more leverage, which delivers usable torque at low engine speeds. That is exactly what a heavy vehicle needs when pulling away from a stop, climbing grades, or cruising quietly for hours. It is composed, it is durable, it is sensible, and it comes with a trade. A long stroke means the piston covers more distance every cycle. As revolutions increase, piston speed rises sharply, inertia builds, friction increases, and efficiency drops. The engine reaches a point where spinning faster adds little value and introduces unnecessary strain for the job it was designed to do. Motorcycle engines take the opposite path. They are oversquare, using wide bores and short strokes. The piston travels less distance per cycle, keeping mean piston speed under control even as revolutions climb. That is why 12,000 or 14,000 RPM is not a stunt. It is a rational outcome of the geometry. The wide bore offers another advantage. It creates room for larger valves and improved airflow. At high speeds, breathing becomes everything. This is not about bragging rights at the red line. It is about maintaining combustion stability as time between cycles shrinks. This difference deserves respect. Car engineers are not ignoring oversquare layouts out of caution or habit. They are optimizing for traffic, load, heat management, and long-term reliability. Motorcycle engineers are solving a different puzzle entirely, working with lighter machines and riders who accept intensity in exchange for performance. Same displacement, same physical laws, divergent goals. Short strokes make high RPM possible, but possibility isn't the same as control. And when everything is moving this fast, one failure point becomes impossible to ignore. That's where we're heading next, into the technology that decides whether those valves actually stay under control at 14,000 RPM. At extreme engine speeds, failure rarely looks dramatic at first. Nothing detonates, nothing shatters. Control simply disappears. The weak point is almost never the crankshaft or the pistons. It is the valves. As revolutions climb, valves must open and close faster and faster, fighting their own inertia every cycle. Traditional valvetrains depend on springs to force those valves shut. That approach works remarkably well until it does not. Eventually, the spring cannot keep up. The valve hesitates, it floats, timing unravels. And when that happens, pistons and valves attempt to occupy the same space. That moment ends races and destroys engines. By the mid-1950s, Ducati engineers were running headfirst into that wall. Racing demanded higher engine speeds, and valve float had become the limiting factor. Stiffer springs delayed the problem, but introduced new ones: heat, friction, accelerated wear. It was a blunt solution to a precise challenge. So Ducati reframed the question: what if the valve was never allowed to close on its own? Instead of relying on spring tension, Ducati designed a system where the camshaft mechanically opens and mechanically closes each valve. No snapback, no delay. Every movement is commanded, not implied. That concept became known as Desmodromic valve actuation. On paper, it appears complicated. In practice, it reflects a clear priority. At very high RPM, control matters more than convenience. Ducati was not chasing novelty or marketing distinction. They were chasing certainty under stress. This system was born on racetracks, refined through failure, and retained because it delivered. Valve float was effectively eliminated. Timing remained precise when everything else was approaching chaos. There were compromises. Manufacturing became more complex. Service demands increased. Springs remained cheaper and sufficient for most engines. But Ducati was never building for most. They were building for the edge. And once valve control stopped being the bottleneck, the ceiling moved quickly. The best way to understand that leap isn't in diagrams or theory, but in the machines that sit right at the edge of what's possible. If engineering like this, more complexity, more maintenance, but absolute control at the limit makes sense to you? Drop a comment and tell us. Would you choose Desmodromic precision for the sake of performance? Or would you rather accept RPM limits in exchange for simplicity and ease of ownership? Because that answer says a lot about how you value engineering under pressure. By this point, the principles are no longer abstract. High engine speed, aggressive geometry, absolute intolerance for unnecessary mass. Those ideas only matter if they survive reality, and they do. You can see it standing still before a single engine fires. Take the Honda CBR 1000RR Fireblade S. On paper, it is already outrageous. 217 horsepower from just under 1 liter, without a turbo or supercharger in sight. But the real achievement is not the number. It is restraint. Every component is there for a reason. The crankshaft is compact. The chassis is tight around the engine. Weight is pulled inward until the motorcycle feels smaller than its displacement suggests. The Fireblade does not overwhelm you with drama. It earns speed through control. That is performance density done with discipline. Now remove the discipline. The Kawasaki Ninja H2R is what happens when the same architecture is allowed to run free. Supercharged, track only, no emissions limits, no concern for longevity beyond the session. Over 300 horsepower from an engine that still fits between a rider's knees, pushing a machine that weighs under 500 pounds. This is not transportation. It is a stress test for physics. The H2R matters because it shows how far motorcycle engines can go before coherence breaks down. And remarkably, it does not. Then there is intent, stripped of spectacle. The Ducati Panigale V4 Superleggera is not chasing records. It is chasing efficiency in the purest sense. Carbon fiber frame, wheels and swing arm, titanium internals, Desmodromic valves working not as heritage, but as necessity. Every ounce saved becomes performance gained. These motorcycles share a quiet truth. They do not rely on displacement to solve problems. They refine motion, reduce inertia, and demand precision. And that philosophy did not appear by accident. To understand why motorcycles committed to it so early, we have to rewind to the moment when speed stopped being a side effect and became the mission. Modern motorcycle engines can feel almost unnatural in their intensity, but that mindset did not appear out of nowhere. It began the moment the industry realized that tradition was no longer an advantage. That moment arrived at the close of the 1960s. Up to that point, high-performance motorcycles were defined largely by British manufacturers. Triumph, Norton, and BSA built machines rich with character and racing heritage. They delivered torque, mechanical honesty, and emotional appeal. But they were also constrained by convention, parallel twins, push-rod valve trains, architectures inherited from a different era of engineering priorities. Then Honda changed the rules with the CB 750. This was not an incremental improvement, it was a redefinition, a transverse inline 4, overhead camshafts, an electric starter, a front disc brake. Most importantly, an engine that remained smooth at speed and welcomed revolutions that previously belonged only on racetracks. The CB 750 was not merely quick, it was dependable. You could ride it hard day after day without treating it like a temperamental relic. That combination shattered the hierarchy. Performance no longer required fragility. Kawasaki absorbed that lesson and chose escalation over restraint. The Kawasaki Z1 did not seek balance, it sought supremacy. More displacement, more output, higher sustained speeds. It embraced the inline 4 and pushed it to the edge of what a production motorcycle could deliver, setting records and earning a reputation that lasted for decades. Together, these machines did more than outperform rivals. They established a new philosophy: compact multi-cylinder engines, comfort with high engine speed, and a willingness to trade low-speed charm for top-end authority. This was not gradual evolution, it was disruption. And here's the key: that way of thinking didn't stay confined to motorcycles. When performance mattered more than comfort or convention, even car manufacturers started borrowing from the same playbook. If motorcycle engines were impressive only in isolation, the argument would remain academic. Interesting, perhaps, but safely contained. But the story gets harder to ignore when car builders adopt these engines intentionally. Not because they are inexpensive, not because they are convenient, but because for certain problems, they are the right solution. In lightweight performance cars, mass is the enemy, and response is everything. In that environment, a compact, high-revving engine is not a compromise. It is an advantage. Look at the Ariel Atom. Early versions relied on Honda motorcycle engines. Mounted in a minimalist car chassis, this was not novelty engineering. It was problem-solving. The Atom did not need low-speed torque, sound insulation, or refinement. It needed immediacy. A powertrain that could deliver violence without dragging unnecessary weight along for the ride. The result was not a car that felt underpowered. It felt alive. Instant throttle response. Enormous power-to-weight ratios. Acceleration that humiliated much larger machines. The same logic appears in the BF Mono. Single seat, track-focused, no pretense of comfort. Its philosophy mirrors that of a superbike. Remove everything that does not directly contribute to performance. A motorcycle-derived engine fits that mission perfectly. And this pattern repeats across motorsport and high-performance builds. Hill climb specials, Formula student cars, time attack machines. Anywhere performance per pound is king, builders consistently reach for motorcycle engines. If this kind of engineering clarity, choosing the right tool instead of the comfortable one, resonates with you, hit the like button. And if you want more breakdowns that explain why these decisions are made instead of just celebrating the results, consider subscribing. That support is what allows us to keep focusing on engineering logic, not surface-level comparisons. This is not desperation, it is clarity. And that clarity brings us to the heart of the trade-offs. Every motorcycle engine accepts choices that car engines can often avoid. Car manufacturers know how to make powerful engines. They also understand the cost in weight, complexity, and inertia. Motorcycle engines offer a different trade, astonishing output from a small, lightweight package at the expense of civility. And that choice always carries consequences, which brings us to the next part, a closer, honest look at the realities of performance, durability, torque, and real-world usability. Up to this point, motorcycle engines can sound almost unfair. Higher engine speed, more power per unit of displacement, extreme output from packages that seem impossibly small, but engineering never gives without taking something in return. Here is where the comparison must become honest. Motorcycle engines live closer to the edge. They spend more of their operating life near their mechanical limits. High RPM does not just unlock power, it multiplies stress. Bearings see more cycles. Valvetrains operate with tighter margins. Service intervals are shorter because physics demands it. That is not a defect. It is a responsibility. Car engines are built around a different promise. Long idle times, stop-and-go traffic, cold starts, infrequent maintenance, years of use without constant attention. They sacrifice peak output in exchange for endurance, smooth torque delivery, and tolerance for neglect. That difference is immediately felt. A car engine feels relaxed. A motorcycle engine feels alert. Torque delivery is another reality check. Motorcycle engines produce their strength higher in the rev range. It is intoxicating, but it requires involvement. Car engines emphasize low-speed torque because it moves mass calmly and predictably. No one wants to downshift multiple gears just to merge with traffic while carrying passengers. Thermal management follows the same logic. Motorcycle engines rely on airflow and shorter duty cycles. Cars operate under heavier loads in confined spaces for far longer periods. Sustaining output there requires thicker components, more cooling, and more weight. Noise emissions and drivability matter too. Car engines are designed to fade into daily life. Motorcycle engines demand participation, and that is the point. Motorcycle engines are not better because car engineers missed something. They are better at one task because they accept compromises. Most cars cannot. Once that is understood, this comparison stops being about winners. It becomes a lesson in priorities. At the start, one word needed precision. Better, not louder, not faster everywhere. Better at a clearly defined task. Motorcycle engines reveal what happens when focus replaces compromise. Freed from everyday expectations, they become lighter, faster, and astonishingly efficient. That is not superiority, it is clarity. And it leaves one open question. How far could this technology really go if nothing else mattered? So no, motorcycle engines aren't better at everything. But when the goal is extracting maximum performance from minimum mass, they show us what internal combustion can really do. If this video made you rethink horsepower numbers, RPM limits, or what engineering excellence actually means, Click the next video and keep going with us. This road trip isn't over yet. Join the tribe by subscribing. If you want to support the channel and get early access to our newest deep dives, become a member. And don't forget to like this video. It tells the algorithm this kind of content matters.